Good afternoon, students. In this class, we are going to see how we can solve linear programming problems involving unrestricted variables. Earlier, the linear programming problems have been solved both by graphical scheme and by simplex scheme by forcing all the variables to be non-negative. Now, if some of the variables go unrestricted, that means it may take either values positive or negative. How to solve the corresponding linear programming problem? That's what we are going to see now. For that, let me take the problem of maximizing a linear function 5x1 plus 10x2 as shown here, subjected to two inequalities, namely 10x1 plus 7x2 less than or equal to 21 and when x1 plus x2 greater than or equal to 1 with x1 positive, x2 alone unrestricted. So, how to solve this problem, that is what we are going to see now. First, we shall proceed to graphical method of solving this problem. As usual, as I already told you, we have to draw a graph with x1 axis here and the x2 axis here. Both are orthogonal to each other or both are perpendicular to each other. Then let us draw the graph for this equation removing the inequality there. Supposing I take x2 0, x1 will be 21 divided by 10, 2.1. So here it is 1, here it is 2, so 2.1 will somewhere be here. This is 2.1 comma 0. Similarly, if I conceal x1, then x2 will be 21 by 7, that is 3. So 3 will be somewhere here. So I have to draw a line graph drawing this 0 comma 3 and 2.1 comma 0. So this is our 0 comma 3. Let me label this as A and this as B. B will be of 2.1 comma 0 and A will be 0 comma 3. 0 comma A will be 0 comma 3. Now coming to next inequality, if I hide this x2, x1 will be 1, that is this point. If I hide x1, x2 will be 1, that is this point. I have to draw in these two lines, call this as C, which is of coordinate 1 comma 0, and this as D, which is of coordinate 0 comma 1. So this is the line joining these graphs. Now, since 10x1 plus 7x2 is less than or equal to 21, we have to draw arrows facing the origin. Since x1 plus x2 greater than or equal to 1, we have to draw arrows away from the origin. So naturally, the feasible region should be CDAB, that is the quadrilateral covered by CD, DA, AB and BC. This is a feasible region. Now, since x2 is unrestricted, the variable x2 is unrestricted, you will have x2 either positive or negative. So let us record that. Since, but x1 is greater than or equal to 0. But x1 is greater than or equal to 0. Therefore, feasible region can fall on either a first quadrant or fourth quadrant, since x2 can assume negative values also. So feasible region in our case is that A, B, C, D. So let us call this meeting point as E. For E, x1 will be positive, whereas x2 will be negative. So the feasible region is extended from ADCB to ADEA, that is ADE. This triangle will be the feasible region, just because of the reason that x2 becomes negative also, both the positive and the negative to be taken up. One may ask that, sir, why do you take this negative quadrant at all? That possesses only x2 positive, x2 negative, whereas in the objective function, the x2 coefficient is only positive. That is not going to maximize anything. Like that many questions can be asked. For that the answer is, simple answer is, if it is 5x1 minus 10x2, then maximization you have to take the negative quantity. If it is the minimization function, this negativity will influence the objective function to be more minimum. So in that case, we need to have this fourth quadrant. And again, the earlierly predicted feasible region A, D, C, B, in the case of both the variables non-negative, extends this feasible region to negative quadrant also, that is fourth quadrant, to have A, D, E as the feasible region, right? Now, already we have A as 0, 3 and D as 0, 1. I already taught you how to solve these two linear equations to have E. So, E I am solving to be, this is 14 by 5 and minus 9 by 5 are the points for E, solved points for E. So, naturally, through graphical method at 0, 3, that is the point A, the value of Z could be 5 multiplied by 0 plus 10 multiplied by 3, answer becomes 30. What will happen to at the point D, point is 0, 1, Z happens to be 5 into x1 value 0 plus 10 into x2 value 1, answer becomes 10. Now at the point where the two lines meet, that is E, for at E the points could be, at E 14 by 5 is the x1 coordinate, x2 coordinate is minus 9 by 5, so the Z value becomes 5 times 14 by 5 plus 10 times minus 9 by 5. So the answer could be 70 by 5 minus 90 by 5 equal to minus 20 by 5, because denominator is the same. So you will have minus 4 as the answer. Since the objective function has plus 10x2, the maximum among all these three quantities could be, maximum of Z will be 30. That is 30, 10 and minus 4. Among this, 30 is the maximum, and against maximum Z turns out to be 30 only. Now how we have solved this problem is through graphical method. Now we have to solve this problem through simplex method. The same problem, maximize Z equal to 5x1 plus 10x2 subjected to, you have 12x1 plus 7x2 less than or equal to 21, together with x1 plus x2 greater than or equal to 1, x1 greater than or equal to 0 and x2 greater than or equal to 0, x2 is unrestricted. Now let us solve this using simplex scheme. Since x2 is unrestricted, x2 can assume either positive or negative value. So, any positive quantity or negative quantity can be expressed as the difference of two positive quantities. Supposing you take 5. 5 can be represented as 10 minus 5. Both 10 and 5 are positive. You take minus 5. Even then it can be represented as 5 minus 10. Both 5 and 10 are positive. So whether it is positive or negative, I can represent through difference of two positive quantities. Using that, I write x2 as x2 dash minus x2 2 dash, where both x2 dash and the x2 2 dash turn out to be positive. Now, the entire simplex problem becomes maximum of Z is 10x1 plus 7 into x2 dash minus x2 2 dash be subjected to the inequalities 10x1 plus 7 into x2 dash minus x2 2 dash less than or equal to 21 together with x1 plus x2 dash minus x2 2 dash greater than or equal to 1. So, introducing slack and surplus variables, we have the entire linear programming problem becomes 10x1 plus 7x2 dash minus 7x2 2 dash, because less than or equal to I will have a slack only s1 equal to 21. Similarly, x1 plus x2 dash minus x2 2 dash, since it is greater than or equal to I will have an artificial variable a1 minus s2 equal to 1. Now, how does that objective function become? Maximum of z equal to 5x1 plus 10x2 then plus 0s1 plus 0s2. So, let us draw a simplex table now, where you need to go for first one is x1, then x2 dash, then x2 2 dash, then s1, then s2 together with a1, then you will have p naught solution column p naught, then ratio column theta j. So, in between p naught and this one the operations are going to take place. So, I block this now, where I have got cost coefficient Cj as x1 for 5, x2 10, then x2 2 dash. So, 10x2, one more thing I have not introduced, minus 10x2 2 dash, minus 10, this is objective function, for which I have my 5 10, then minus 10, 0, then 0 0, then minus m dash. Now, I have basis and the cost basis here. For that, let me substitute the basic coefficient, that is 10, 7, minus 7, then 1 1, then minus 1. So, x1 x2 dash and x2 2 dash filled. S1 coefficient in the first inequality is 1, S2 coefficient 0, A1 0, then P naught column 21. Then I have S1 coefficient in second inequality is 0, S2 is minus 1, and A1 coefficient 1. Then corresponding P naught column I will have 1. So, next one I need to go for the computation of Zj minus Ej, where I will have unit matrix available in S1 and A1 column. So, let me put S1 here and A1 here. S1 cost is 0, A1 cost is minus m. Right. So, I will have Zj minus Ej now, that is to be xb cb minus Ej. That means 0 into 10, 0, minus m minus 5, minus m minus 5, then minus m minus 10, minus m minus 10. Then you will have positive quantity. Then here you will have 0, here you will have positive, here you will have 0, here dash. The most negative quantity is this much. P naught column divided by pivot column. This is the pivot column, most negative pivot column. 21 by 7 becomes 3, 1 divided by 1 becomes 1, among which this is the least, 1 is the least. So, naturally A1 leaves and A1 leaves, x2 dash enters, x2 dash enters. So, replacing A1 by x2 dash, I will have x2 dash cost as 10, Then what is a pivot element here? Pivot element is this. So this A1 in the first A1 row in the first table becomes the old pivot row. Old pivot row by pivot element gives you the same entries 1, 1, minus 1, 0, minus 1, 1, 1. Then but for the A1 I will have S1. S1 cost is assumed taken to be 0 because S1 Cj is 0. Then I have to make this entry to be 0. That means the place at which the old pivot row comes, that is to be made as 0, for which we have to make use of the earlier S1 row. So multiply this by 7 and subtract, this will be 0. So 10 multiplied by 7 into 1, 3. 7 multiplied by 7 into 1, 0. Minus 7 multiplied by 7 into minus 1 becomes 0, because minus 7 minus of minus 7. 1 minus 7 into 0 is 1. 0 minus 7 into minus 1 is 7. 0 into 7 into 1 is minus 7. 21 minus 7 into 1 is 14. So I need to compute once again Zj minus Cj. So Zj minus Cj becomes 10 minus 5 is positive, then 10 minus 10 becomes 0, minus 10 minus of minus 10 0, then 0 minus 0 0, then minus 10 minus 0, minus 10, then I will have 0, 10, this become positive and this is dash. So once again I will have negative entry in the Zj minus Cj. This becomes the pivot column here. Now P0 column divided by pivot column gives negative here. 1 by minus 1 is negative. 4 by 7 is 2, and hence now S1 leaves and S2 enters. Now we have to perform the next table, where I will furnish this next table at the left side of this paper for convenience. P0 and CB only. So I block this. Then I will write the cost coefficients available in the objective function, that is already 5, 10, minus 10, then S1 coefficient 0, S2 coefficient 0, then A1 coefficient minus M with a dash here. Now since S1 leaves, and what I simply do is I will put S2 here, whose cost in the objective function is 0. Now our pivot element is this intersection of pivot row and pivot column, 7. I divide every quantity by 7 and write here. That is, this is 3 by 7. Then I will have 0 by 7, 0, 0 by 7, 0, 1 by 7, 1 by 7, 7 by 7, 1. Then minus 7 by 7 is minus 1, 14 by 7 is 2. Then but for this S1 row being replaced by S2 now, other quantity existing is X2 dash, whose cost in the subjective function is 10. Now I have to make this entry 0. That is S2, X2 dash intersection. X2 dash is this, S2 is this element intersection to be 0. So what I need to do is simple addition, minus 1 plus 1 will be 0. So simple addition between these two. 1 plus 3 by 7, 10 by 7, then 1 plus 0, 1, then 0 plus 1 by 7, 1 by 7, then 1 plus minus 1, 0, then 1 minus 1, 0, then 1 plus 2, 3. Now what do I do is, I have to go for computation of Zj minus Cj. So 100 by 7 minus 5, that is positive. then 10 minus 10 becomes 0, then minus 10 minus half minus 10 0, then 10 by 7 minus 0 positive, then 0 minus 0 0, then 0 minus half minus 1 positive, so dash. Now what happens here is all Zj minus Ej becomes positive. Therefore, iterations end. Therefore, the value of Z becomes 0 into 2 plus 10 into 3 will become 30. And again 30 is the maximum value of the subjective function for this linear programming problem, which tallies with the graphical method having 30 as the maximum value Z, right. So, in that way we prove that both graphical solution and simplex solutions provides the same answer for maximizing the linear function Z equal to 5x1 plus 10x2. Before going to next problem, let me have certain things here. That is, number one is that the unrestricted variable problems can be solved using graphical method and simplex method also if we have only two independent variables. If we have three or more independent variables, graphical solutions may not be successful. In that case, we will go to simplex method only to solve this. So, whatever be the number of unrestricted variables, we need not worry about it. All these unrestricted variables must be written as difference of two positive quantities, and those two positive quantities need to be substituted in the objective function as well in the inequalities to complete the structure of the linear programming problem before entering into the simplex method. Once we enter into simplex method, naturally all basic variables will have the basic variables as they appear in the problem together with the introduction of unrestricted variable will come into place. All other procedures in the simplex method are one and the same with respect to big M method. So, when we said all Zj minus Cj becomes positive, we end the iterations and we substitute the values of the basic variables applying in the basic variable basis column and the P naught column, correspondingly multiply the Cb and the P naught and add to declare the answer. So, this is the idea behind the unrestricted variable role in a linear programming problem, whether they are having either less than or equal to symbol or greater than or equal to symbol in the constraints section. So, if at all you use unrestricted variable in the constraints, the same unrestricted variable is to brought up to objective function also, so as to make sense that both the positive quantities can influence the objective function. That is the idea behind it. So, we shall continue with this next method in this next class. Till then, I request all of you to go through the both graphical and the simplex method to make it thorough, so that when unrestricted variable come into play, how to solve this using either simplex method or graphical method could be well known. Thank you.